So thank you for coming, even though the title of the talk was literally just Numba. Hopefully that didn't deter you or make you wonder, what is this word I keep hearing people say? Are they just saying number funny? Yeah, no, this is a real project. So a good place to start is why Python for high performance computing. And the reason I start here is I have this discussion with people all the time who are accustomed to, I come from a science background and our go-to languages were Fortran and then later C++. And so people would always ask me, why on earth would you use Python? Isn't Python slow? It's an interpreted language. All of the sort of traditional rubric you learn about how different languages are, Python seems to be the worst choice for high performance computing. But it's actually turned out to be surprisingly effective for two reasons. One is it's easy to use. It fits into people's brains well. It's easy to pick up. It's easy to pick up if you're not a professional programmer, but someone who needs to program to get another job done. And the second thing, and this is the one that's not talked about as much, is ease of extension. Because of some design choices made in Python, it's tremendously easier to connect Python to other things that may have been written in another language that is designed for high performance. And so it's not about, a lot of people get into the mindset that you need one language to rule everything, and you don't necessarily. Sometimes you have to live in a world where you do some bits of code in C or even assembly or Fortran or whatever, and all of the libraries in Python that you know and love, under the hood, are delegating a lot of the high performance work to things like NumPy, NumPy and SciPy are delegating to things like C++ and Fortran. A lot of SciPy was basically take all of this amazing Fortran code that's been crafted over decades and make it connected to Python so that you can get work done. And all of these things contain this. So if you were doing data science in Python, you were also benefiting from these other high performance libraries. However, switching languages does have a cost. It means that there are fewer people who can write high performance code. It means that you sometimes have to delegate it off to someone, or, okay, so some of these times these codes exist, but sometimes you need to make new stuff. What happens when you need to write a new algorithm for your research? And then the question starts to come up of, what if I could extend Python with Python? In a sense, not just saying, well, I'm just going to run this through the interpreter, but I'm going to maybe do something else with it to make it go faster. And as soon as you ask this question, you have a bunch of trade-offs and hard problems to solve. Do you replace the whole interpreter? Do you just say, I'm just going to throw out CPython? CPython is the traditional Python implementation written in C, hence the name. There are several others. Do I compile ahead of time or not? Do I add this build step to users? Do I need a C++ compiler to be present at runtime? Do I translate the whole program? Do I work with smaller units like functions or modules? Do I only target the CPU? Do I target other unusual hardware? There's no correct answer to any of these things, and every choice you make is going to have consequences for the user experience and also for how much performance you can achieve. And so this is my, not Magic Quadrant, because this is a judgment-free quadrant. There isn't a corner of here that is better than the other corners. They're just different. And the two, this is a 17-dimensional problem, but one way I like to think about them is when am I compiling and what am I compiling is basically the two approaches. And there have been tons of Python projects. There are a bunch that aren't even on this list. And so you can look at these things and think about, okay, what are the choices being made? If I want to do just-in-time compilation of the whole program, PyPy is an amazing project. I would suggest you go look at PyPy. There are a lot of problems you can solve with PyPy that you can't solve with Numba. But it makes the choice to do the whole program, and that has consequences. Versus ahead-of-time systems like Shedskin and Nutka, which more or less take your Python code and translate it into C++ that makes some calls into the Python library, but effectively gets rid of the whole interpreter loop and all of that. Then you shift to the other side of this plot where you talk about functions. In this case, you're just saying there are some performance critical pieces of my code I want to compile. I don't care about the rest. And then you have options like Cython, which is well-established, well-loved, is effectively a way for you to ahead of time compile pieces of your program. Still using CPython, you haven't replaced it, Pythran. And Numba lives up in this other corner where we're trying to do just-in-time compilation of individual functions. And that's sort of how you think about us in relation to all the other choices. And depending on what you're doing, you may need things in different ones of these boxes. So the Numba compiler in the shortest but perhaps hardest to unpack statement is a type specializing JIT compiler for Python functions. Type specializing is important because this is effectively the secret sauce for how Numba gets performance. Is Python by default is dynamically typed. can pass in a number or an array or a list or whatever, and a lot of functions will just adapt to whatever it is you pass in and do the sum operation in the way you would expect. The problem with that is that every time you do that, it has to go through a whole dispatch decision tree kind of thing to figure out for every single thing you operate on at every value in the program, what is this thing and what is the actual machine code operation I need to do to implement it. What Numba is doing is basically to look at when you pass something into a compiled function, what are the arguments, and then I'm going to go make a special implementation just for those types. And then I'm going to remember that, and the next time you call, I'm just going to go call that. Or if you come back with different types, I'll make a different representation and call that. And this is what allows Numba to achieve much, much higher performance than something like traditional Python because it can do this type specialization. The other key is that it is just in time, meaning that when you start up, Python or Numba doesn't know what types you're going to use. It's an interactive language. You might be using it in a Jupyter notebook. At the moment you call the function, we will figure out what those types are and then do that specialization. And it's only for Python functions. You don't compile the whole program. You should actively not try and compile every function in your program. That's both not necessarily going to work and also not a good use of compute time. Most of your code is going to be performance bound on a few things, not everything. Another key design requirement for Numba was to be able to work from within the standard Python interpreter. There are consequences for leaving that interpreter in terms of the PyData ecosystem. People are going to still want to be able to use scikit-learn and that weird compiled Fortran and some other stuff. And all of those things have been plugged into CPython. If Numba said, nope, throw all that away, you're going to go live in your own little world and we'll just try and compile everything, that's a very hard problem to solve, and it's ultimately would cut us off from a lot of the innovation happening in the rest of the PyData ecosystem. The other key piece is that Numba is not the whole compiler. It is effectively the front end to a compiler, and that underlying back end is LLVM, which you may have heard about from the C++ compiler Clang uses LLVM. LLVM is very popular, and it really is what allows Numba to run on many different kinds of hardware, is we can take advantage of the fact that everyone is basically making their hardware work with LLVM. Our main focus is on scientific and numerical code. If you're trying to do really like complex string processing or very, I would say, sort of object graph web application kind of stuff, Numba's not going to be a good fit. There's a lot of hard problems to solve, and we've focused specifically on use cases involving numbers and loops and that sort of kind of thing that you're doing. And really what we're trying to do is bridge the high-level programming feel of Python with the high performance that you can get from things like Fortran and C. So the way Numba works is that there are various entry points into the Numba compiler system. Effectively, our interface are decorators. These are, in Python, these are things that you can put above a function which basically transform the function into something else. And by judicious application of these, you can take your code and say, this function I want to compile, I'm writing a special kind of function here, maybe I'm going to run this one on the GPU. There's a whole family of these I'll talk about. And what those do is those wrap the function in something that will, as soon as you call it the first time, will set off a whole compilation process. We'll do some code analysis, we'll look at the types and figure out every type of everything in this function we're trying to compile so we know if it's a float or an int or what kind of float, all that stuff. And then the output of that analysis is something that is fed into the code generation step, which emits machine code. And we use different LLVM or LLVM-like libraries in order to target different platforms. So there's the standard LLVM, which we use for CPU. NVIDIA has a fork of LLVM called NVVM, which they use for GPU code. For the AMD target, we sometimes use a different version of LLVM, depending on what's most appropriate for the GPU. But this sort of fundamental structure is what Numba does. And as a result, we can target a lot of different platforms. So Numba has I would say sometimes terrifyingly large build and test system because I need one of every computer on Earth, more or less. I don't have MIPS yet, if someone knows where I can get one of those. But we have, we test on 32-bit x86, 64-bit x86, ARM version 7, which is the 32-bit you might be familiar with from the Raspberry Pi, ARM v8, the 64-bit variant of that, Power 8, NVIDIA GPUs, AMD GPUs, Windows, Mac, and Linux, all the different versions of Python, Python 2.7 still for now, although Python 2.7 is coming to end of life and we will be dropping it along with everyone else. But yeah, so Numba, one of Numba's core tenets is we need to be able to run everywhere if people can depend on it, and that's something that we take very seriously. And on the user side, it's a family of compilers. Numba is not just a compiler, it is a toolbox for building compilers, of which we have built now, I guess, 7 vaguely related compilers. One is the traditional JIT for compiling Python functions, runs on the CPU, fairly intuitive. The next 2 are for building special kinds of functions that, if you're familiar with NumPy, you may have seen the universal function or the ufunc. Vectorize and GUvectorize let you build certain kinds of ufuncs very easily so that you can generate these sorts of array operations with a lot less code than if you had to do it in C. Stencil is a contribution from Intel to help do neighborhood calculations. This is if you're trying to do things like convolutions, windows, that sort of thing. They kind of feel like ufuncs, but they are inherently around sort of calculating something for a window that you are going to slide over an input. cfunc is an interesting one. One of the use cases for Numba that you may have heard mentioned in the keynote is for user-defined functions. I have an existing compiled system, maybe it's in C++, maybe it's in whatever, and I want to have the user write a little bit of code in Python and then take that code and embed it into my existing system. In that case, you need a stable C signature to call from this other system. This other system might say, hey, give me an objective function for my optimizer, and it needs to have this signature. In Numba, we don't, normally when you're using JIT, the underlying machine signature is totally hidden from you. You don't care, you're calling from Python. With cfunc, we kind of crack open the hood a little bit and let you say, okay, literally, what signature do you want to call this from in C? And that's what we'll match. And when we do that, you can then grab the pointer from that compiled function and hand it off to this external system. And we have people who are actually using this capability in production, where their data scientists build code that runs in their production system using cfunc to basically expose it into a larger C++ runtime. And then the last 2 are the GPU targets, where we can compile both CUDA kernels for NVIDIA and ROCm kernels for AMD. So one of the most important things I have when I teach people how to use Numba or talk about Numba is to remind people that Numba will not compile everything. And it's really important to think about it as one of the mental models you have to build is when is Numba a good idea and when is it not? And Numba is a good idea in a number of situations. I won't talk through all of them, but I'll talk through a lot of them. And one of them is you're trying to do some fast prototyping. Maybe your end target is not necessarily to, by the way, this is all that's required here to get a lot of speed up. So this is the best typical case I could possibly show you, of course. But yeah, I like that term too. But the basic idea here is we want to make it easy for you to quickly try out an idea, but also not have to wait for it to run forever. And so if you were thinking, geez, I'm going to have to go reach out and grab some C++ or do some other thing, or maybe you're just in a notebook and you're like, man, I just need to try this out and I want this function to go fast, you can just, this is running in a notebook, it'll just JIT this function and it'll run quite a bit faster. Another place where we've seen people is that they'd like to avoid writing some Fortran. Fortran's a great language, I've written a lot of it, however, sometimes I just don't want to go there. And so we jokingly referred to Numba as rehashing the entire history of Fortran. So if Numba from like 3 years ago was like Fortran 77, then the next year we might have hit Fortran 90, and then just in sort of as we added more programming constructs. And so a lot of our target audience is trying to write the sort of hardcore numerical algorithms you would have reached for Fortran for, and instead here you want to write it in something that looks like I'm writing NumPy in Python code. This comes from, was adapted by Stuart Archibald, one of the Numba developers. And you get some advantages here that you switch from Fortran to Numba is that you do get the advantages of generic typing. You can write one algorithm, and when it comes in with float 32, we'll compile for float 32. And when you comes in with float 64, we'll compile with float 64. You don't necessarily need to worry about things like templates or all of the other mess you'd have to do this if you're just using Fortran. You're getting to use the NumPy API instead of BLAS, which may be more convenient. We also handle things like memory management and stuff for you and all of those things you would expect from something that looks like Python. And the net result is something that is about as fast as the Fortran code. This is the target. Numba is not magic. It will not make your code run faster than something like Fortran or a very highly tuned algorithm. What we want you to do is get to this goal with less writing and less cognitive load. And that's really our goal. And even, at one point someone was doing something like, this code is 25% slower than Fortran. And we did a little dance because we were like, that is awesome. Because where you were starting from was 100 times slower than Fortran. The fact that we were only 25% slower than Fortran meant that you could get your work done and you didn't have to do a whole bunch of work. Other things that we've added in more recent years, this is thanks to a contribution from Intel, is making it easier to do some basic parallelization without having to worry about p-threads and all that stuff. Interestingly, what we heard from numerous users is that an interface that they really, really like is effectively sort of like OpenMP, where you have a for loop, but you've marked it as a for loop that you want to run in parallel, meaning every iteration of the loop is independent of every other iteration, and so the system is free to schedule each iteration to whatever thread pool you have access to. And so in order to enable this compilation mode, you have to first tell the JIT, okay, parallelization's okay, go ahead, start up some threads. This parallel accelerator, as it's called, will go through and also try and optimize your array expressions automatically. So even if you didn't write a for loop, it'll try and run all the array expressions in parallel, which can be very helpful. If you're familiar with numexpr, this is in that vein. But also if you want to do some explicit parallelization, and here this p range is basically like range, but it tells Numba, oh, do this loop in parallel. And here you can see, this is just a 4-core machine, but you could imagine if you have 8 or 16 or 28 core machines, you're probably not getting a lot of use out of them if you're just using pure NumPy, but here you might be able to make better use of them. And we are experimenting with different threading backends because they have slightly different versions, but again, it doesn't matter a whole lot if you came down from the single-threaded runtime to any of the multi-threaded backends, you're pretty happy. As I mentioned, another common use case is user-defined functions. On the left, we have cfunc for the CPU. On the right, we have rapids using the same kind of approach, but instead for the GPU. And this is becoming more and more common. We expect to see things like databases and other analytics engines potentially bridging the gap between Python and whatever their runtime is using Numba as a user-defined function compiler. And this was an interesting one. We personally never actually thought about this, but we had someone come to us and say, hey, I'm thinking about switching from Python to Numba, and we thought, why? Your Python code looks totally fine. And they said, actually, I'm tired of having to compile my package to post wheels, which I thought was interesting. That by using Numba to do all the JIT compilation, your code stays pure Python and has no compilation step for the user, which makes it potentially easier for you to distribute and all of that. Now, to do that, you have to, of course, trust Numba to have tested thoroughly on all these platforms, and that is a trust we take very seriously, and we try very, very hard. Every release, actually, every time we update master, we test Numba on some like 250 different combinations of Python, NumPy, operating system, hardware. It kind of is a little out of control, and sometimes we feel like we need to pare that back a bit. But it also helps if you can't actually try all this hardware. A lot of times we see developers are like, I don't have a Windows machine. You might not have a Power 8 machine. You might not have an ARM. And so, well, you probably have an ARM, but you might not have an ARM processor. And so they ask all these things, and so this is another thing that we can do is at runtime select the best instructions. So different generations of Intel processor get more and more parallel instructions. And if you as a packager have to build for a particular, what do you pick? My user might be using a Pentium 3. I actually had that in a tutorial. I was like, I didn't know that any of those laptops still function, but they do. If you take care of them, I guess. Or you might be on a server with AVX 512. What are you going to build for? And this just makes you as a packager go crazy. And so just-in-time compilation can be one solution out of this. So let's talk about who uses Numba. And this is just a small subset. But one of the things I'm going to emphasize in this list are libraries that other people use. And one of the things we really hope to see Numba doing is not just be a target for end users building applications. There are tons of scientific applications I've learned about that are using Numba that literally the scientists are using to accelerate some of their algorithms. But we're also starting to see it getting adopted by libraries that then other people use. So for example, if you've used the UMAP library, UMAP uses Numba to accelerate some of the algorithms inside. And the beautiful part about this is that as a UMAP user, you didn't have to worry about what we could compile or any of that stuff. You just benefited from a faster package. Another one of those, this is our personal favorite just because we have a soft spot for music analysis, is Librosa. They were also a very early adopter of Numba, and we got a lot of good feedback from them. And this is a package built by researchers who are doing, effectively analysis of music as audio and looking for things like chords and notes and passages. And so they wanted to think about the algorithm, how do I find this thing in whatever analysis method I'm using, but I don't want to worry about how to make fast code, and I really don't want to worry about how to ship fast code. And so they picked up Numba to be able to write basically the loop that you wanted to write in Python, but would be 100 times slower. HPAT is another one. This comes from Intel Labs. They are looking at how to basically dynamically compile entire pandas workflows. So in a function, you might be loading data from HDF5, doing some NumPy operations, doing some pandas operations, and then you want to be able to run this on an MPI cluster. HPAT is effectively a special compiler, a specialized panda compiler built on top of the Numba compiler. They they plug into all the hooks that Numba provides to build new compilers and built a special one. And so this is a really interesting application. And as a result, a number of the HPAT developers are now actually core Numba developers because of the amount of contribution they had to make to the Numba core to support this. And the final one for this is OAMAP, which is near and dear to my heart coming from particle physics, in which they were trying to, there's a whole, I would say, movement in that world to try and figure out how to use C++ maybe a little bit less as a user-facing analysis. And this is basically, again, using Numba to be able to more directly take user code that looks object-oriented, but map it onto an underlying array data structure, which is very efficient. All right, so a lot of that is what Numba is. Let's talk about where Numba's at, because you may have heard about Numba in the past, but may not have noticed some of the things that have been added recently. One of them, and I'm just going to step through a couple that I think are really interesting, is GDB integration. One of the major focuses we've had over the last year is, now that we've really zeroed in on what use cases Numba is to be good at, how do we help users be more productive? And a lot of those things are around things like debugging and error messages and all the stuff you heard in the keynote this morning, so it was really good to hear that reinforced. One of the problems you have is if you're trying to debug a compiled function, how do you do that? Because PDB isn't going to work. PDB assumes the interpreter. You're going to have to go to something like GDB, a tool designed to debug compiled code. What is the interface between GDB and sitting in Python? And this is something that we realized no one had really solved well, so we went ahead and solved it. And the goal here is to basically make launching GDB from inside of a compiled function as easy as launching PDB is. It's even, I guess, shorter with the old syntax for PDB. It works in threaded code. It actually shows you Python source lines, not some kind of assembly dump or something that won't make any sense. You can inspect variables using Python names. Scalars we can show you pretty reasonably. Structures don't look so good at this point, but they can get better. One note, for technical reasons we haven't been able to figure out, you can't do this from inside of Jupyter. If there is some Jupyter expert, we would love to talk to you about how to make this work. But you also can launch GDB from outside of Numba. You could launch it from the Python interpreter, and we've had some super advanced users and developers actually use it for that and not about using it inside compiled GDB. Another one, and this is a long time coming, and we had a lot of debate about this, about how to expose it in a way that would not put the users into a trap, I guess, is the ability to jump out of compiled code in the middle of a function back into interpreted code. There's always going to be something that Numba cannot compile, and acknowledging that we live in this mixed world, we're going to have to decide, how do we want to let you do that in a way that's not going to cause the performance of the function to be completely unpredictable to you, the author? So for example, you could say, well, what if every line you decided to jump back and say, I'm not going to compile this line, but I will compile this line. The result is that little subtle changes to your code would cause factors of 10 swings in performance, and you'd get very frustrated and probably just throw Numba out. So what we opted for was something where you do have to tell us you want to go back into object mode, but once you do that, anything you do in this block here, in this case, this with object mode context manager, you can do whatever you want. You want to call back to a progress bar, you want to go update a GUI, any of these things we can't compile, you can do that. A recent addition was C callbacks with structs. We had people who said, hey, I like your cfunc compiler, but I need to actually pass in a pointer to a complex C struct. It's not just an array of values or anything like that. We've added support for that. So if you're looking to integrate Numba into more complex systems, this may help you. As was mentioned earlier, interop with CuPy and PyTorch has been a focus. We can now pass CuPy GPU arrays and PyTorch tensors directly into Numba compiled CUDA functions. As a result, we're telling people, hey, CuPy is great if you just wish you had GPU accelerated NumPy, and then come to Numba when you want to build a function that CuPy doesn't have. And actually, there's a tutorial there that I gave a few weeks ago all about Numba and CuPy on the GPU, if you'd like to learn more. Strings. Strings were one we held out on a long, long time because we felt like stay focused on numbers, but as data frames have become more popular, we couldn't ignore strings. And there's a lot of places to grow. You may not appreciate it, but the Python developers have spent years and years and years fine-tuning the string implementations in CPython to a razor edge. It is extremely hard to beat Python. So much like Fortran, we can only aspire to be as fast as individual implementations of algorithms from Python. But our goal here is to basically make it so that if you need to do some string work in the middle of a larger function, you have that ability. And really importantly, when you pass a string in, we don't copy it. We just take a view onto the internal Python storage. Swappable thread backends. And I'll skip over to this one, SVML autovectorization. So one of the things that we try and do is when you write a for loop, basically all of the modern CPUs you're using now have the ability to run instructions that operate on multiple values simultaneously. These are called SIMD instructions. And they're a real key component of getting max performance. It's not just about how many cores you have, it's also if you can use the SIMD instructions. And LLVM can do some automatic generation of this, but it tends to stumble on math functions because they're not just a simple addition or multiplication or division. And so Intel ships a library which, if we detect it at runtime, which actually implements vectorized versions of math functions you would probably want to do, like cosine, exponential, hyperbolic tangents, all of these sorts of standard special math functions. And when this is enabled, we will be able to automatically vectorize uses of those functions in loops or in array expressions. And so this was a huge deal for getting additional performance out of machines. You do all this extra work, and then this get another factor of 2 to 4, and that's pretty awesome. ARM support. This was another FAQ. We love the Raspberry Pi. You probably love the Raspberry Pi. Why not Numba on a Raspberry Pi? And we've actually been tinkering with this for years and years. The issue we opened to add this was like 2.5 years old or something. It was like one of the oldest issues we finally closed last year. And so now we have support for ARM v7, which is the Raspberry Pi 2 and 3. If you haven't seen Conda, it is a unofficial Conda distribution for the Raspberry Pi. And so we actually build Numba packages that you can use with Conda directly. We're looking into the pip wheel situation, but it's a little bit confused on ARM, and so we haven't found a good place to put it. ARM v8 you may be familiar with from specifically some of the newer NVIDIA sort of IoT boards, the Jetson TX2. We actually build and test on Numba on a Jetson TX2. The Nano is effectively the same architecture, we just don't have it in our build system yet, so we haven't tried it out. CUDA works too. I would say, however, this is something to look forward to the future. It's really tricky to install. We built just enough infrastructure to verify for us that it works there, but the user experience to get it installed on ARM v8 is not good yet, and that's something we're still looking at. And then finally, and there should be like explosions and fireworks here, is dictionaries. This is probably the #1 thing people have been asking for since like 5 minutes after Numba was posted, is dictionaries. Dictionaries, aside from arrays, dictionaries are the best data structure. So we've been thinking very hard about how to do this, and we are taking the steps required towards it. So in the last release, we have the ability to now use what I would call a statically typed dictionary. So you have to tell us up front what type the key is and what type the value is. In the future, we'll do the type inference for you, so you will just figure it out from your code in most cases. It still has to be one thing. You can't make a dictionary that's one key's an int, another key's a float, another key's a whatever. That we can't generate fast code. You're back to basically what Python does. But the implementation is basically straight from Python 3.7. Item retrieval can be inlined. Basically, we can, if you're in a loop looking up stuff in a dictionary, it will run somewhere between 2 and 10 times faster. both insertion and lookup. So if you are doing, again, mostly numerical code and you need a lookup table, you now have some tools for that. All right, let's talk about the future. So those are things you may not have noticed that we've done recently. Where are we going? So the constant sort of march is towards Numba 1.0. We release every 6 to 8 weeks. So you may like think our version numbers are kind of silly. We just released Numba 0.43. That means there have been literally 43 releases of Numba since it started 6 years ago. And we do 4 or 5 a year because we want to get things out to you faster. What is, how long is this going to go? Am I going to be coming back in 3 years and telling you about Numba 0.98? Hopefully not. And so what is required to get there? The first thing is we've reached the point now where we need to pay off some tech debt. The way that we did lists and set support back in 2015, we've now realized is not the right way to approach it. We're going to go back and do it the way we did dictionaries. This is a big one. Numba has another compilation mode that we try not to talk about, but people trip over all the time, which is in which we don't generate type specialized code. We just unroll the interpreter loop and call back into CPython a lot. And it was built at a time when we thought we would have more mixed code, where it was more of a mix of compiled and sort of less compiled code. But it's just a huge user experience nightmare. And so we are going to be taking it out as an automatic fallback. You will have to opt into it if you need it, and you shouldn't opt into it. We're also going to be working on caching. Another thing that people are saying is, hey, Numba's great, I'm using it everywhere. Oh my gosh, starting up my program takes too long because I'm JIT compiling like hundreds of functions. And so we want to be able to cache those compiled functions to disk. It's a capability we have today. It's not turned on by default because we know there are limitations to it. We have to remove those limitations and then turn it on. We're also looking for more GPU interop opportunities. Another thing that we're trying to do is make it easier to contribute to Numba. Compilers are intimidating for people, and one of Numba's goals, aside from making compilers more usable, is to make the whole thing more accessible to new developers. And that's something we want to do, and of course, the looming deprecation of Python 2.7. After Numba 1.0, then maybe things get a little more interesting. People talk about the other after dictionaries. Everyone wants us to be able to compile classes. We have very limited support for that today. We're going to have to rethink how that works. Object orientation is a whole rabbit hole that we have to figure out how to navigate. A lot of people are wanting to do more ahead of time compilation, where they're saying, the JIT is nice, but in production, I actually can't even take the time to compile. I want it to be compiled and fixed on disk, and we have to think about how to architect that. There's also starting to open the door to partial compilation. Some kinds of Python code that's very dynamic, we can't compile because we can't resolve all the types up front. It's not just like Fortran written in Python. In that case, we need a way to do partial compilation. Compile the function up to the point where we don't know what's going on yet, and then wait until runtime, and then do more compilation at that point. And then better interop with other languages. This is something that always comes up. C++ is a big one. There's obviously C++ has come out of dormancy with C++ 11, 14, 17, all of that. We need a better story to talk to C++. And then, I don't know, what other languages are people wanting to interface to? Julia comes up a lot. JVM languages, R. I mean, there's a lot of possibility here to think about. Another one is GPU target unification. So we support AMD GPUs and NVIDIA GPUs. You may have noticed that there may be some other GPUs coming out in the future from other manufacturers. Eventually, all these targets are going to have a lot of code to support each one of them. There's a lot we could do to combine and share code underneath. We don't want to become OpenCL 3.0 or something, but we could at least make it easier to add new targets like that. Another one that comes up, if you see Peter Wang wandering around, ask him to tell you about why Python should run in your browser directly. And so we get a lot of requests for WebAssembly as a potential way to compile code to run directly in the browser. So in conclusion, Numba is a really powerful tool to have in your high-performance Python toolbox. We don't want to be everything for everyone, but we want to be something very useful for a lot of people. It works on many platforms. We've expanded out from pure numerics into strings and dictionaries in the last year. There are a bunch of quality of life improvements that we've implemented already and more that are in progress. A few deprecations are coming in the near future, so keep an eye out on the release notes. We will give many deprecation warning cycles before we change anything out on you. And we are just going to be continuing the march to 1.0. So thanks.